engineering, specialized in earthquake and geotechnical engineering with extensive experience in soil structure interactions. He's the head of dynamic department at Terrasol Tech Group since 2019. And he's going to give a presentation today. You can start your presentation now, Jared.
Do you see my screen?
Yes.
Yes, okay, perfect. Thank you very much for the invitation and for the kind introduction. So I'm going to talk to you about a topic is more related to the design and prevention. So it's related to earthquakes. So it's about displacement-based approaches, especially for seismic design of geotechnical structures. So Terrasol, we are a geotechnical consulting company. We're about 85 engineers and experts. We are mostly located in France, in Paris, Lyon, and Bordeaux. We have today around 30% of our activity, which is outside France, and we try to participate as much as possible in the scientific community. That the reason we try to produce around 20 to 30 articles per year, articles in international conferences or in some reviews. So our participation to scientific activities is try to participate to all the broad spectrum of the scientific community. So it concerns all the professional associations like the International Society of Soil Mechanics and Geotechnical Engineering, participate to normalization groups such as Eurocodes. We do a lot of training and education inside the company, but also outside. So we participate in most of the French engineering schools, giving some different lessons about different topics, mostly related to geotechnical problems. And of course, we participate to different research projects, mostly in France, but also in some international research projects. And this allows us to do also some part of our activities. We develop in-house software to deal with different geotechnical problems. For example, the design of foundations, to deal with stability problems, design of retaining walls, or the assessment of liquefaction risk. So this is something we develop because when we deal with some of the problems we study every day, we try to innovate, to give innovative solutions to our clients, and step by step, sometimes we arrive to develop some tools that sometime later may become professional grade software that, in the case of different softwares, so for example, these 4 softwares that I saw you on the screen, we commercialize and we offer to to the professional community to study different geotechnical problems. So today we of course deal with we intervene in different steps of different geotechnical problems, mostly in design, but also in the reevaluation of existing structures. So today, one of the main problems we need to address is, for example, the assessment of the resilience of the structures that are part of some critical infrastructures. So today we try to take into account the more and more extreme external hazards. And for the topic of today, I just focus on earthquakes, but as you know, we have already heard in the beginning of the session, we have a broad panel of external hazards and needs to be taken into account. So if, for example, we take a look at the problem of a bridge that is part of a transportation infrastructure, if we deal with extreme earthquakes and, for example, it's an existing structure that we need to reevaluate and to for example, conduct a risk assessment. If we look at the problem and we try to analyze what are the tools, the approaches that are available today in the engineering world, I'm not talking about research, but more focus on what we actually will do for the design and reevaluation in a design company. We find that we have two very different approaches. We have, of course, access to full 3D nonlinear analysis that give us a lot of liberty and the possibility to model very complex topics, very complex constitutive laws, very complex geometries, which is something that we can do for very important projects where we have the resources, we have the time, we can mobilize all that is needed to model very extreme problems. And on the other part of the spectrum, what we are going to find is what we apply to most of the design and study of the structures are more classical approaches, what we usually call engineering approaches that are mostly based on substructure schemes, where we, in most cases, we use linear models and to determine the response of the structure, to determine the forces, the moments, and all the verifications are based on pseudostatic verification formulations. So as I saw in the screen, for example, for the case of a bridge, we'll get the forces and moments at the base of each one of the piles. And if we intend to verify the varying capacity, we could use, for example, the verification criteria that is given in Eurocode. If we respect the criteria, that means we are stable. If we don't respect it, that means that we have an instability problem. What we observe here is that we have two approaches that are very different and then doesn't demand the same amount of energy to address the same question. And it is not always possible to use the direct full 3D full analysis. So from the engineering perspective, it is obvious that we need intermediate approaches that need to be simple to build, capable to take into account some of the problems that cannot be taken into account in the classical way we have addressed these problems. For example, all the nonlinear effects. And of course, if we want to assess to do a risk assessment of the structure, we need to conduct parametric studies. So we need to have some intermediate models between the full 3D model and the substructuring approach that in theory doesn't allow us to go beyond the nonlinear limits. This is something that in earthquakes, just to recall, I think most of you are already aware of. There are some particularities because of the type of the loading in seismic. When we deal with seismic loading, so the static failure doesn't imply seismic failure. When we deal with static and permanent loading, if we have an excessive load, that is going to generate a failure. It's generally what we verify is that the safety factor is always higher than 1. But when we are dealing with seismic loading, if we have excessive load, that means that we are going to have permanent and irreversible displacements. But that it doesn't necessarily mean that the structure is going to we are going to have a failure of the structure. So we need to redefine the way we define the limits of this type of problem in terms of permanent displacements instead of safety factor. So that is to say, we need new approaches that allow us not only to verify in a force approach, just verify in terms of safety factor, but to verify what are the displacements that are introduced when we apply this extreme load to our structure. So we need a nonlinear, in this case, we need to conduct nonlinear SSI analysis but an intermediate approach, not to have a lot of difficulty or a very expensive approach that is, if we only have this type of approaches, we could not use it in most of the structures. That's one of the reasons.
Excuse me, can you hear me? Is that possible to finish the presentation in about 5 minutes?
Yes, yes.
We go over time a lot, and I think.
I understand.
Thank you very much.
Yes, so this is one of the reasons we have. It has motivated us to develop a new in-house software. So the idea is not that innovative, something that has already been done in the research community, but the idea here is to apply to customary design of the structures. So to model the structure in a simplified way, by means of stick models that allow us to take into account the response of the structure, the soil structure interaction. We can continue to model it in the classical way, introducing, for example, by means of springs and dashpots. And the newest thing that we introduce is all the non-linear phenomena that are going to take place in the interface between the foundation and the soil. That means in the case of a shallow foundation, that it's going to be a sliding, the loss of bearing capacity on uplift. So the way we introduce that is by using what we call microelements, which is something that has been developed for the case of shallow foundations, mostly in the last 2 decades. Something there are a lot of research that is already available. And what we have done is what we look at the literature, what we find is that there are a lot of models that are offered, but they always need some calibration steps. They need to calibrate some different parameters. The only different thing we have done is that we have tried to use as much as possible all these already available criteria that we already have, for example, in design codes. That's the reason we use, for example, for the bearing capacity, the same criteria that is given in Euro code. For the sliding, but this is a simple criteria. And to model uplift, we try to model this as simple as possible. It translates just to model a nonlinear law relating the moment to the rotation at the base of the structure. These developments have already been done several years ago, so we have already had the opportunity to use it in some of our studies. This is, for example, the study of sensitive installation in the nuclear industry, for which, when we conduct the classical approach, the forced verification approach, we apply the criteria given in Eurocode. What we observe is that we cannot verify the stability of the structure. It doesn't mean the structure is going to be unstable. It only means that the structure, because of the application of the seismic loading, is going to experience permanent displacements. So now that we have this type of models, we can conduct transient nonlinear analysis that allow us to calculate these permanent displacements. So here, for example, in the case we have no nonlinear phenomena at the base, we have this result, and when we introduce the nonlinear behavior at the interface between the foundation and the soil, of course, we are going to experience displacements, and the main effect it's going to have on the structure is that by construction, it's going to isolate somehow the structure, because it can the interface cannot transmit far from the limits the higher solicitation than the limit at the interface. And the only thing that needs to be verified is that the displacement that are induced by this by the loading are compatible with the structure. So in this case, for example, what we observed that we have displacement that were as much as 1 millimeter, which is something that is for this structure was, of course, not a problem. So we could verify that the structure was going to experience some displacements under seismic loading, but were not, its stability was guaranteed. This type of studies, we can find it in literature. So this here is also another study that you can find in literature. It's just a conclusion showing that if we conduct this SSI studies at each step, introducing, for example, changing from fixed phase to linear SSI, then introducing sliding, loss of bearing capacity, etc. At this step, we see that we increase the safety of the structure, and the only thing we have to verify is that the induced displacements are compatible with the structure. So here, as you see, if we, for the most critical case, we introduce all the nonlinearities, the maximum displacement is around 115 centimeters, which is, we only have to verify that the structure is capable of admitting this displacement. This is for shallow foundations. We can find a lot of research today. So when we, at this point, we were able to conduct the analysis for shallow foundations. So we asked ourselves, the question was, what could we do if we have deep foundations, pile group? So after a little research, we find that there was already some developments available in the literature. So mainly in the last decade, which concern mainly single piles. So the idea is to introduce also a macro element, and in order to develop that, we started a PhD study. The objective was to study the dynamic soil structure interaction of pile foundations and to combine experimental numerical and experimental numerical approach to verify in the first step the nonlinear seismic response of this type of foundations, and then to develop a macro element. So we conduct experimental test at the University Gustave Eiffel centrifuge that we compared to numerical simulations, and we use all this data to develop and validate new pile group macro elements. With this new development, now the possibilities are open to study the response of different type of structures, to see how they evolve when we change different parameters. So we can conduct different parametric studies. So just pass very quickly. And today, the same question is asked for another type of foundations, is for structures that are founded on soil reinforced by rigid inclusions. So we have started a PhD study in collaboration with the National Research Project RCD+. So the idea is to develop also a new macro element to take into account this kind of phenomena, and to validate this numerical and theoretical development and compare it to some of the experimental research that is already been taking place at the University Gustave Eiffel centrifuge within the framework of these research projects. So this is something that is ongoing today. And just to say very quickly, it's a concept that has already been tested and it's already been used today. So the example of the Rion anterior bridge, which was by design founded on rigid inclusions, and the idea was to isolate the structure by allowing the sliding of the base of the piles. It's very interesting because the structure has already been subjected to an earthquake, and what you see in the screen is the displacement of the base of one of the pylons. As you see, it was designed for a displacement of 2 meters. So here you see that has already well behaved. And the interesting point here is just to highlight again that in these studies, in the design studies, they also used experimental approach to verify some of the numerical designs. And just to show here, it was a test to verify the burying capacity of the foundation, also conducted on centrifuge. And that shows the importance of combining experimental, numerical, and theoretical developments in order to develop all this type of models. And just to finish, just to say that if we see this problem from the design perspective, what we need today is to have intermediate approaches that allow us to, if we want to conduct risk assessments of or structures to be in design or structures that are already available, we need to have different levels of sophistication of the different tools for this study in order to be able to conduct parametric studies and see the importance of different parameters. Thank you very much for your attention.
Thank you. Okay, thanks, Yanis.
Just a quick comment. I'm Yanis Anastasopoulos from ETH. Thank you for a very nice presentation. As you know, the GeoLab project is offering so-called translational access. So, and the next round will be on validation of numerical models. So I think that what you are doing fits like a glove, let's say, to the next round. So I would invite you to consider applying for a proposal to, let's say, to validate some of your numerical analysis with centrifuge testing. You will have to go outside France, I think, but correct, Ton? Yeah. Yeah, but Cambridge and also ETH do offer these capabilities. There are shakers, so if you would like to discuss anything more, please feel free to contact us.
Okay, I think that's also a nice conclusion for this workshop, because the whole point is trying to offer our facility to innovations from, especially from industries. And I think now we really have to go to the coffee break, and I'm really sorry about this long presentation, but it was really interesting, and thanks a lot for contribution from all the presenters.